Welcome to UGC EPG Pathshala in the course of Linguistics. I am Somnath Roy. I will be speaking on recognition of spoken word part 2. This module has been written by Dr. Samudra Vijaya K. I will be speaking on behalf of him. So we'll be looking at the following content: introduction, a recognition of sequential patterns, challenges in matching of sequential patterns, dynamic time warping, and dynamic time warping for connected word recognition, and followed by summary. So in machine recognition of speech, it is very difficult if we have to linearly match, or if we have to do template matching for word recognition. So in this module, we'll discuss how the recognition of spoken words need to consider varying speaking rate into account. We'll introduce dynamic time warping technique with the help of illustrations of its application to spell checking problem. And finally, we'll try to show how such a template matching technique can be extended to continuous speech by preparing reference template for all words in the language. Besides, these templates should take into account a large number of variations inherent in the speech spoken by different persons under various acoustic environment. So looking at the recognition of sequential pattern, let's say if we have a speech signal and if we compute their MFCC, or the feature vector, so we'll have 39 dimensional feature vector, and if I am representing those feature vector as xi to xn, let's say, so we'll have xi to xn as a feature vector computed from ith short segment of the input speech. And if we have to match the template, so we have computed, let's say, if we have to detect whether this is the sound or not. So if we have computed all the feature vectors for all those sort of sounds, and if we have stored it somewhere, and now we have another sound, which is one of the sounds stored there based on the feature vectors. So, and now we want to check whether this test sound is one of the sounds stored there or not. Then this, if we are going to use the same, we extract that feature vector from the test speech, and we look into whether this is matching. We compute the difference. Let's say difference between all the speech stored in the template. So continuing with the recognition of sequential pattern, in this case, we select a problem of recognizing a spoken word for illustrating the challenges in the task of recognizing a sequential pattern. An example in this case is name dialing. Let's say if you want to speak to your friend on the mobile, so if you just say call Atul or call somebody, then that phone should call, just dial that number. So we just want that name should be recognized by the mobile. That is our task that we want to build, and this kind of pattern is called recognizing a name, or name dialing. Building a name dialing system is a sequential pattern. So when you speak the name of a friend near a mobile phone, the input speech data is processed to compute a sequence of MFCC like feature vectors. So let's say the sequence is from x1 to xn, where xi is the feature vector, computed from ith short segment of input speech. Here n is the length of the sequence and depends on the duration of the utterance. The process of recognition is as follows. The feature vector sequence computed just now is called the test sequence, okay, which you want to get recognized. It's compared with the reference feature sequences of all words known to the ASR system. So in the name dialing example, the reference feature sequences were computed in advance from spoken names of your friends. one reference sequence for each friend. So the phone calls that friend whose reference number is closest, that is matches the best to the test sequence, will be called. So such a procedure of finding the reference sequence that matches the best with the test sequence is called template matching. But in template matching, the core task is to compute the similarity between reference sequence, let's say y1 to ym of length m, and the test sequence of length x1 to xn of length n. So if the length of two sequences are equal, then we are at good place. So one can compute the distance between these sequences by summing the distance between pair of feature vector and computing the square root as root under I equal to 1 to n sigma mod of xi minus yi whole square. However, in many cases, a difficulty arises when the length of test sequence is not equal to that of reference sequence. So now, how we are going to take the difference, pairwise difference between those input features. So in this case, what happens while comparing a short spoken word, say Ram, with long spoken word, say Duryodhan, then it is not clear which pair of feature vectors have to be considered for pairwise distance computation. So another sequence of unequal length of reference and test sequence is when a given word spoken slowly, let's say some elder person, is to be compared with same word spoken rapidly. In other words, speaking rate can cause unequal length when the same word is spoken by different person. One simple solution to this problem is to normalize the length of reference sequence with that of the test sequence. If the length of reference sequence is, let's say, 150 feature vectors and the length of test is, let's say, 100, then one can drop every third feature vector of the reference sequence. Then the length of reference as well as the test become the same. So on the other hand, if the reference sequence is shorter than the test sequence, a few frames of reference sequence can be repeated. Such proportional warping of reference sequence so that its length become equal to that of the test sequence is called linear warping. However, linear warping is not enough. Linear warping method fails in many cases due to varying speaking rate within a word. For example, a speaker might have stressed a syllable, resulting in relatively longer duration of that syllable. So, in that case, we need a mechanism called non-linear warping of a reference sequence with the test sequence. So, this non-linear warping, which is also called dynamic time warping, is based on dynamic programming technique, and a step-by-step process of this dynamic time warping is shown below using a spell checking and correction mechanism. So as you can see, a spell checker and a spell checking and correction is used to show the dynamic time warping procedure. So as you can see, if you write in word file some word which is incorrect, then you will see a red wavy line below that word. So and then you right click on that word and you will see all the matching words, best probable words that can be replaced by the wrong of the wrong word that is written there as a substitute to that wrong word. So how that comes into the into there? So thanks to dynamic programming, and dynamic programming is utilized for this in this dynamic time warping, and this is nothing but as you can see, let's say if you have typed the text called pattern and the spelling that you have used is PPATARRN. So what I am going to say is, let's say if first letter is, if we have written a letter correctly, then the cost is 0. If there is a vowel and we have written a different vowel, then the cost is 1. If there is a consonant and we have written a different consonant in that place, then it is distance is 1. If there is a consonant and there is a vowel, then distance is 2. So this is how we measure the distance in this. So as you can see, this diagram, figure 12, this is a grid where we have used, the correct, incorrect pattern, incorrect word typed on the horizontal axis and correct on the vertical axis. So if you see, the first word is P with corresponding to P, so there is 0. But if you see the second one, this is, there should be A, but it has been written as P. So the cost is, it is vowel is substituted by some consonant, so there is distance is 2. That way it's the matrix is built. And now we'll this is a formula of dynamic programming. Capital dxy is equals to a small dxy plus minimum of dx minus 1 comma y comma dx minus 1 comma y minus 1 comma dx comma y minus 1. So it's just look into its neighborhood, and whatever is minimum, it just pick that path. So this is a dynamic programming approach through which we compute, from which we trace the path from the leftmost lowest point to the rightmost highest point, and the optimal path, which has lowest cost, is considered as the optimal one for finding the result. So the same process is followed for dynamic time warping for connected word recognition. And what is the takeaway of this lecture is, you need to look into deep into what dynamic programming itself is, and then you can relate this dynamic time warping with the spoken word recognition. So moreover, we can say that dynamic time warping is one of the technique that uses principle of dynamic programming to efficiently compute the least distance between the test sequence and the reference sequence by optimally aligning them. And the principle of such sequence matching approach was illustrated by application to spell checking problem. So you can match this spell checking problem with as a sort of example to get the notion of what dynamic time warping is and how it can be used, or how it is being used in continuous spoken word recognition. So in this lecture we have seen that what is how the alignment of test and reference set can be a problem in template matching, and template matching needs linear time warping is not enough, so we need dynamic time warping, and dynamic time warping is based on dynamic programming, which is one of the very good algorithm used in many computer science branches and artificial intelligence. Thank you.